Good afternoon. Thank you very much for joining us to one of the last webinars that we're going to do now on the Mobilise project, the Mobilise algorithms and in Python. So our colleagues here, and especially Arne, will present you the pipeline and then the algorithms that you could use later in your research, in your developments, and also what are the use cases and how we use them in the Mobilise project. Without further ado, I give the word to my colleague to present you this. How we are going to run it will be a presentation, a couple of demonstrations, and then we are going to have questions and answers. Thank you very much. Arne, it's your turn.
Okay. Perfect. Thank you very much for the introduction, Mara. You should all be seeing my screen now. Yeah, my name is Arne. I'm a researcher at the Machine Learning Data Analytics Lab at the Friedrich-Alexander University in Erlangen-Nürnberg. So that we understand the context, I will give you a brief introduction to Mobilise and then a brief introduction to what we've built, and I'm going to go into a little bit more technical demos. So as I guess most of you know, if you're here, this is part of the Mobilise-D project, which is one of the largest efforts to get mobility measures established as clinical endpoints, as digital mobility outcomes that can be used in pharmaceutical trials or as clinical endpoints for various treatments. It's funded by the EU via the IMI projects with a quite substantial funding amount of 25 million euros that was matched generously by our industrial partners. The co-leads of the consortium that you might be already familiar with, of course, Professor Lynn Rochester from the University of Newcastle, and joined for the past couple of years, Dr. Daniel Brooks from Novartis. And we have, of course, this entire consortium of experts of the domain. So basically, if you're working in a project, you're basically interacting with everyone that has been doing gait and mobility research in Europe over the past years. The goal, as stated here, is that we want to connect digital mobility assessments to clinical outcomes for regularly in clinical endorsement. And one key component of that, and that was the work that Work Package 2 and Work Package 3 focused on, was to identify and evaluate the best possible algorithm pipeline for a lower back IMU sensor. And this work was roughly structured into 3 parts, starting with the pre-technical validation study, which was at the very beginning of the project, where we took already pre-existing data sets from the community to do initial testing and optimize algorithms that we either got from publications, got from partners within the project, or needed to re-implement based on our algorithm structure. With these pre-optimized and pre-selected algorithms, we went into the technical validation study, where we had laboratory assessments with gold standard camera-based systems, as well as free-living unsupervised home monitoring with something that we with a multimodal IMU system as a ground truth. With that was one of the first and largest data sets that had reliable ground truths for out-of-lab gait recordings, which was great to completely validate every aspect of our algorithm pipelines. With kind of the validated algorithms, we then went into the clinical validation study, which is the majority of the project, the largest undertaking, with thousands of patients that are followed either for 2 or 3 year period, every 6 months, with a continuous 7-day recording using the IMU sensors and the algorithms that we validated to see if there are relevant clinical correlations or relevant correlations between clinical measures and the IMU signals that we record. Just as a reminder, as part of at the end of the technical validation study, we came up and validated a pipeline that looks like that. The most important feature here is that it's actually 2 pipelines. So what we found out is that depending on the severity of the gait impairment, and we basically categorize that by clinical indication, one pipeline seemed to be working better than the others. In particular, the initial detection of gait sequences and how cadence was calculated was like better done with different algorithms. We evaluated these algorithmic steps individually. If you're interested in more information about that, you can see the paper by Encana. And we validated the entire pipeline output, so running everything end to end which you can find more about in a paper by Cameron Kirk, which was published this year. I will not talk about like what these algorithms do in detail. Today's webinar is focused on how we're gonna use the software abstractions of these algorithms and how we interact with that. But if you're interested to go more into detail and just have a refresher, we have webinars just like that one today on our YouTube channel. In particular, the first one is focused on how these individual algorithmic steps work and the science behind it. So let's go more on the technical side. What we built originally in Mobilise-D looks like this onion of complicated pieces of technology. The algorithms themselves were a combination of Python, MATLAB, and Java. The reason for that was relatively simple. We set out to compare all algorithms that we could reasonably find and compare, which was over 80 individual algorithms. So at the beginning of the project, it was not feasible to take the time to re-implement everything in a common language, make sure that we followed common code guidelines or anything like that. We need to make sure that we get as many algorithms running so that we can do a proper comparison and make sure that we didn't miss an important algorithm just because it was not implemented in the language that we expected. So what we did as part of work package 3 was to build a unified runtime based on multiple virtualization layers of Docker containers that were run in an AWS, so Amazon-based cloud service that was then controlled by an open source project developed by the University of Newcastle, which is called eScience Central, which we used for managing our data as well as running these algorithm pipelines. This served its purpose, and that's very important to get us going. But now that we are nearing the end of the project and we want these algorithms to be one of the core legacies of the Mobilise-D project, we need to make sure that everyone, everywhere can run these algorithms in a correct and easy way. And having like a layer upon layer of virtualization setup is definitely not easy to set up. And having proprietary software like the MATLAB as a core component makes it more difficult for commercial use cases. And of course, even for many academic use cases, as MATLAB licenses are not as ubiquitously available anymore. So what we did over the past 6 months, so basically that was the task that I led, is to do a re-implementation. And that re-implementation is called MobGap. MobGap, or the Mobility and Gait Analysis package, is a Python package fully developed in Python with a unified implementation that is inspired by, I call it our sister project, GateMap. GateMap is a library that my team at FAU has developed over the past couple of years, focusing on gait analysis algorithms for foot-worn IMUs. But we use that as a blueprint so that we could start with something that was already proven to be working, just structural-wise, and people enjoyed using, and used a lot of the concepts that we developed there, just as the foundation for the new Mobilise algorithms. The most important part is that everything was done in the public, right? So that you could follow the development, and you can still follow the development publicly on our GitHub repository. So how does this look like in a little bit more detail? Over the past 6 to 8 months, we re-implemented the 15 core algorithms and extensive tooling around it. Extensive tooling around it means we focused on making sure that you are able to load and standardize data that we published in Mobilise, and that you are able to pre-process data that you might have so that it fulfills the requirements of our pipeline. At the same time, we built a validation framework so that you can validate the individual outputs of the blocks or the outputs of the entire pipeline in the same way that we validated our algorithms as part of the technical validation study. The hope here is that we can standardize some of these procedures, or at least make reporting them easier and more uniform, because this is often a source of a lot of like unclear reporting and papers, and often a source of like unknown errors, maybe as simple as train test leaks in like a machine learning context, but also like the definitions of how we define a true positive in certain senses is often not that clear. And we hope by having a unified framework, we can solve a lot of these problems. If you go to GitHub, and I'm going to do that in a moment to show you the page, how you would view it once you end up on GitHub, you will be able to find the package, the download instructions, and everything else. And at this point, it's important to mention that, of course, this was not just me, right? So this was a team effort by an amazing group of people that come from like all the different labs within Mobilise that contributed to this development. And we hope that that we can continue these developments even over, like after the project of Mobilise officially ends, and maybe be able to add like one of your names to the list, because at the end it's an open source project. Okay, an open source Python package, what exactly does this mean for me? First of all, open source in this case means we publish the package under an Apache 2 license, which is very liberal. Of course, not official legal advice, but basically speaking, you can do whatever you want with that as long as you reference the original package. This means you could even modify it, use it in your commercial product, could, like, of course, use it in any form of research that you're doing. The second thing, because we are working in the open, right? We felt the need to follow best practices, make sure that this is similar to what you might already know when it comes to working with Python packages. In particular, we were inspired by scikit-learn. You will see that later on, that we followed a lot of the interfaces. But it's open source, and open source goes both ways, right? By putting it out there without any expectations of, without any expectations and control, we also expect you to, when you're working with the algorithms, to, first of all, hopefully give us credit so that we can spread the word. And also, in case you encounter issues or have improvements that you like to make, to contribute them back so that this package can grow as a fundamental building block of our research community. And what we hope is that it can go beyond Mobilise, in the sense that we provided plots that you could use even if you're not working directly with the Mobilise pipeline, but if you're just building pipelines, evaluating or testing new algorithms in the domain of mobility analysis. Okay, here comes a disclaimer. This means we are getting close to the slides that I want to show, and we're going to jump in a couple of demos. It's quite important disclaimer. Of course, we want to thank the IMI and the EU of funding that, but of course, everything that I already said I'm going to say is the opinion of myself and the Mobilise Consortium, and not the IMI, our funding partner. But while we are on topic of disclaimers, I have two more disclaimers before we go into the examples that I want to show. First of all, what you are going to show you is better software, right? Open source projects are in a continuous development process, and this one in particular is not quite finished. We set out to finish it end of June, which is quickly approaching, but it's not quite there. So we have a couple of weeks to iron out a couple of issues. This means in particular, if you're watching the recording of that on YouTube, make sure that you check the up-to-date information and the most recent information that we publish with the package, and don't try to directly run code that I'm going to show here. It might not work the same way, or things might not be named the same way anymore. So just make sure that you always reference to official documentation and not just the code I show here. The second thing, and that's also quite important, while we validated the conceptual algorithms as part of the technical validation study, now that we re-implemented them, because we switched programming languages for many of them, and of course we fixed a couple of bugs and ironed out a couple of problems that we saw on the go, we need to revalidate them in the same way so that we can confirm the performance ranges that we originally reported. That has not been done yet. So if you're using these algorithms in your research, just be aware that the performance ranges that we report in recent papers might not be 100% applicable anymore. We're quite confident that what we have now are the best possible implementations of these algorithms, so we assume they perform as well or better as the old implementations, but there's just no official confirmation of that. Okay, with these disclaimers out of the way, I'm going to close the presentation, and we're going to jump in to what you would see if you end up on our Mobilise GitHub page. This is that. I locked out of everything so that this is the experience that you will have when you end up here. So if you worked with Python before, then this should be familiar, right? The folder structure, what we did here, that should be very, very standard if you look at any other Python package on GitHub. We followed as much as possible modern and established best practices. Our code is extensively tested. This means we did manual testing and as well as unit testing, integration testing, so everything that you would expect from a software development project on that scale. But ideally, like, you will not be spending a lot of time looking at this GitHub page and our code. Just what this is, it's a software package that you can install. So if you scroll down and follow the install instructions, that is basically what you should need to have a mobgap available in your local Python project. And then ideally, if everything goes right, you spend the majority of your time afterwards on our documentation, which you can find linked up here. So the documentation page should give you an overview of what is available. And I'm going to just jump through a couple of things so that you get a feeling of the scale of the project. We have user guides, which start with a Q&A with common issues and common questions that you might have. Things that are directly targeted at you want to use your own data. This means there's a guide on the data types that we expect, on the coordinate system that we expect, so that if you have custom data, you can make sure, oh, okay, does my data align with these expectations? Because otherwise they might not be able to work with all the algorithms. We have an extensive set of examples showing everything from data loading, how to use the entire pipelines, individual algorithms, and general tooling like data transformations and so on. And of course, like, we have the box standard documentation, which is the API references, which gives you for each of the algorithm groups an overview over the algorithms that we have implemented, additional tooling that we have implemented. And if we look at individual algorithms, you can see parameters that these algorithms might have, and short explanation how the algorithm works. Potentially relatively important, a detailed description of where we need to deviate from the original implementation or the original paper. And basically the methods and procedures that you can use the algorithm for. With that, let's jump into a couple of examples. I want to start with a couple of examples that I personally find very cool, in the sense that this is what we built this entire package for, as basically the use cases that we that were really difficult before, but now come relatively simple with having all these things in place. The first thing is the entire technical validation study in 6 lines of code. What do I mean by that? So the technical validation study is 115 participants that did like extensive in the lab and outer recordings. And in the past, with all our layers on wrappers, it was quite complicated to run the entire pipeline structure on all of the participants. And it also took quite a long time. If I remember correctly, it was about 26 hours to rerun all the algorithms on all the pipelines. Now, we can not only abstract a lot of the complexity of the data structures and also how the algorithms work away by loading the data set in 1 line of code, initializing the algorithm pipeline in another, and then using very standard Python as a for loop to loop over all recordings in the data set and get the results that we want. But this also happens much, much faster, even without specific performance initialization, because we don't have the overhead of running these virtualized containers. We can now run this entire thing on my 7-year-old laptop in around 30 minutes, which enables an entire new possibility of iteration and playing around with this data. Of course, 30 minutes are still too long to show in this webinar, but luckily, because of the way we standardized everything, I can basically jump from the TVS dataset to a piece of example data that we are shipping with the package by just changing 1 line of code. Now, instead of using the TVS data that I had stored on my computer, we can use the example dataset, which is much, much smaller. And I can actually run this code here. And we can see that we are processing the 9 recordings that are part of the example dataset. You might get a warning here and there, but these are most of the time helpful because they should probably inform you that you need to be careful with certain things. Right? So this processes our 9 example recordings, and what we get out is a data frame of all the individual walking bouts that were detected and then parameterized for all the participants. You can see we only have 3 participants in this example data, all the measurements and all the tests that were part of that. So this is the TVS in 6 lines of code. And the 2 magic things here are, if I want to change how things work, for example, let's say I want to see how a different gate sequence detection algorithm applied to the healthy adults would affect the results. I could change like yet another line by adding, after the initialization of the pipeline, by adding a call to set parameters, I can modify what gate sequence detection algorithm is used under the hood for the pipeline applied to the healthy participants. The syntax is very much inspired by the scikit-learn pipeline syntax. If you're familiar with that, that should be relatively easy to get going. With that, we can just change this. And now, of course, you will not directly see a major difference, but now we're running the other gate sequence detection algorithm under the hood. And this could also be one of your algorithms if you follow the same standardization and abstraction that we use. So this is not just specific for algorithms that we specifically developed in Mobilise. You can see we detected a bunch, we detected less walking bouts as we did before. So this algorithm didn't seem to be like a relatively good choice for this piece of data. So let's get rid of that again. We run it again and ask kind of the next important question, right? TVS was not just running the algorithm, TVS was also evaluating it. So how good are these results and how do we figure it out? What we built in MobGap is kind of a relatively general and uniform evaluation framework for not just digital mobility outcomes, but sensor outcomes in general. For that, the first important thing is we need reference data in the same format that our pipeline outputs look like. The data set that we shipped, the example data set, and also the TVS data set, and your data potentially as well, has reference parameters available. We can just quickly load them in the same way that we ran the pipeline, we loop over the data set, and then we get the reference parameters also formatted in a very similar way. So you can see we have the same column names, the same structure, but this is the information from the ground truth of this data set. So there are different ways of how we could evaluate this. I'm going to show one way, and that's an approach that we also choose in the publication by Cameron Kirk about the full algorithm evaluation, to evaluate only walking bouts that were detected by both systems. And this is a surprisingly complicated process to efficiently identify all the walking bouts that have a certain overlap or large. We abstract that away by basically calling a function that we implemented called categorize intervals that can do exactly that. But we don't want to accidentally match information between this participant and this participant. So we just simply group. So we basically using pandas as the standard library, and behind that, we simply group our data by our index columns and then apply this categorization. And in a second step, extract only the intervals that are true positive matches. And what we get out here is basically a subset of the walking bouts that we had before, and the data frame that has both pieces of information combined. So we have all the parameters and we have the information from the detected and the reference system. So this could also already be helpful for some quick manual comparison, but realistically, we want to calculate errors, like proper error values for that. We developed an extension for kind of the typical pandas aggregate apply terminology that allows us to declaratively define what columns should, what errors we want to calculate for what columns. So just looking at that, it should be hopefully directly clear what errors we want to calculate and how to extend that to calculate errors for other columns or other error values. You can even extend this with error functions that you've written yourself if you want to do a little bit more esoteric stuff. So if you apply that, we directly get the, as defined up here, the absolute error, the relative error for the cadence, and all the error metrics for stride length, and the absolute error for the duration. This is, of course, not the end of everything, right? These are individual values per walking bout. The final step that we need to do is to aggregate everything. And we can decide to either aggregate over all the walking bouts that we see here, or aggregate per participant, aggregate per cohort, and so on. Independent of that, we basically designed a little framework that can abstract away how these aggregations are applied. Similar to how we define what errors are applied, we can define that we want the mean and the standard deviation for all the error metrics calculated for stride lengths, the same for all the error metrics calculated for the cadence and for the duration. And in addition of that, we calculate something that's usually a little bit more complicated to calculate in such a context. We calculate the interclass correlation between the detected and the reference values for cadence and stride lengths. And now, if we just want to apply it across the entire data frame, we just use the apply aggregation function and just format the resulting information of it. Right? And now we have final error metrics, like you would report them in the paper. And I did that all on the lab example data set. But if it would scroll up and would have half an hour of time, I could just switch that out for the TVS data set and would get the same data frame with the final results, basically following the same procedure that we used in the paper to run the comparison. If I don't want to aggregate over all of that, again, we are working with pandas data frames under the hood. So I just throw group by cohort in between, and I get a value for healthy adults and MS separately. This, like, if you did a validation like that, you know that this can be quite difficult, right? And usually, because it's so difficult, people don't really attempt to go more into detail to do a lot of more elaborate things. But because this took like 50 lines of code, I think we have the confidence to go a little bit further and to do something a little bit more complicated. Let's try to optimize things, right? So I've already showed you that a lot of these algorithms, just switch back to the documentation real quick. A lot of these algorithms have a bunch of different parameters. Like these are all parameters that are set to predefined values, right? But they could also be modified, and probably there are better values to choose depending on the data set, depending on a lot of other factors. So often we need to optimize these parameters, and ideally we should do that by some automatic process, a grid search, for example. We can do that with what we build in MobGap. We just throw all the validation that I just showed into a function, right? So that we can easily apply it multiple times. So this is basically what I just showed you, but a little bit simplified. We're only going to focus on the absolute error of the stride length, just now basically wrapped in a function. And because we only want to fine-tune an algorithm that is specific for the healthy pipeline, we're going to just choose a subset of the data, which is just the healthy adults. There was a question, what happens if an algorithm misses a walking bout? So the evaluation that I showed here was tried to match to walking bouts, and the evaluation only worked on the walking bouts that were detected by both systems. To make this a complete evaluation, we would also need additional ways of evaluating basically how many walking bouts were detected, how many were missed, and so on. If you're interested in that, I would really suggest to read the paper by Cameron Kirk, where we kind of explain that procedure step by step. But just know that this is possible. I just shorten the example a little. Okay, we want to optimize things. Let's bring it back to here. We're only looking at the healthy pipeline. We're only looking at the healthy participants within our example data. And we can quickly test our scoring. So I provide the pipeline and just one recording from the healthy pipeline to the scoring function. And just so we see the output once, okay, it's a dictionary that has the mean as expected with a value. So we have an error of 14 centimeters. Let's do a grid search. It's as simple as bringing in our grid search helper from our supporting library called TPCP. That's also the foundation for GateMap and other libraries that our lab has built. We define a parameter grid and we run a grid search, right? So as simple as that, we are now trying out 3 different parameters for the gate sequence duration, one of the parameters of our underlying algorithms, right? And we get, as an output, we get, it takes a second. But then we get as output the parameter that we modified and the performance. And we can see that on average, going to a smaller value here seem to improve on this specific data set, the performance a little bit. But you might ask, okay, that's not doing that properly, right? We're probably overfitting this parameter on a data set. What we should really doing is a cross-validation, of course, but this is only like one other line away. We just import cross-validation and run the same procedure that we had before in a cross-validation, right? So if you have not done like an algorithm comparison like that, then this might seem like, yeah, that's how things should be done. That's how people describe it in papers. They say, we ran a grid search, we ran a cross-validation step by step. But because a lot of the algorithms that we're usually working with don't fit in these unified frameworks like scikit-learn and others, this takes a lot of manual work, a lot of deep understanding of how these procedures work, and are common sources of errors where people might not correctly implement some of these aspects. What we build here abstracts away a lot of this complexity while still allowing you to deeply modify how the pipeline works, what errors you want to calculate, and so on. This is, of course, like the super high level cool stuff that you might be able to build with that. What I want to do for like the next 15 minutes is to go like a step back and focus on, I guess, the two things that most of you are most interested in. Taking the algorithms, and in particular, the entire pipelines that we build, and apply it potentially to your data. If this works, I would invite you to look at all the cool other stuff that we built, but I guess that should be the core focus. Okay, so let's look at running algorithms. And for that, we first need to understand how the data that I just magically had loaded in the background and things like that works. So we're going to load this example data set again that I was talking about. And you can see this example data set holds an index of basically what recordings are available. And we can select just one of them, like this. So just one recording from one of the MS participants. This is an instance of a Python class that has a bunch of attributes that describe the actual pieces of data that are associated with the recording. For example, the single sensor data can be loaded like that. And we can quickly plot it. So this is just the pandas data frame, and we can see it looks like IMU data. In the same way, we have participant metadata. Participant metadata could be the height of the participants, the weight, and so on. And certain pieces of this information is also required to run specific algorithms that we have. For example, our straight length algorithms, as I will show later, require the leg length or the sensor height as an additional input parameter to correctly calculate their internal inverted pendulum model. And we have the sampling rate as well. I would just load that here as well. So it's just 100, so that we can use that as a variable later on. What I'm going to show now is a quick extract of how to run a couple of algorithms. If you want to know what algorithms are available, I best head to the API references, look at the algorithm block that you're interested in, for example, initial contact detection. Click on the algorithms that you're interested in, and then you can see parameters, so things that you can modify about the algorithm works up here. And then the most important thing is all the algorithms have an action method. The action method for initial contact detection are detect. Detect here tells us what data requirements do we have. So what pieces of data do I need for this algorithm to run? And for a simple algorithm like this initial contact detection, I basically just need my IMU data formatted as a pandas data frame and my sampling rate. For other algorithms, for example, like the stride length algorithm I was talking about here, we can see that the action method, which is called calculate, takes the data, takes initial contacts that were already identified, potentially by a previous step or extracted from a ground truth reference, the sampling rate, and also the sensor height in meter to fit the internal biomechanical model. So let's just run through a couple of these algorithms. And if you're interested how they would be used in sequence step by step without the abstraction of a pipeline, we have an example that is called step-by-step pipeline, which I will show in a second, where we go through them one by one, how they would be used in real pipeline. For now, just run a gate sequence detection algorithm. This one, GSD eloads. We just import it, initialize it, and here's the point where we could change parameters. So here I could add window length and change it to something else. And then we could call the action method with our IMU data and our sampling rate, and then results are available via attributes on the results. So this is very similar to how scikit-learn works as well. And here we just run the algorithm, and get the start and the end in samples of all the algorithms. As I mentioned, we could change parameters. So let's just change the gate sequence duration. Then we can see we get slightly, in this case, okay, we don't really get any different outputs because it didn't change much. But if we, for example, increase it further, then we see we find much fewer gate sequences because we have that minimum gate sequence length. And then we could also go deeper. Some of these algorithms basically have nested subcomponents. So their GSD-ELOS algorithm has a pre-processing filter, which in of itself is an algorithm object. And I could just provide a different algorithm object to it, change the filter order and the cutoff frequency and provide that. You will see that this is not a good idea. So this joins a lot of gate sequences, which might not what we want. But I just want to show you that we have the option to configure and modify these things. Now we have a gate sequence. Let's run an initial contact detection. Initial contact detections and most algorithms after the gate sequence detection are designed to run only on individual gate sequences, so not on the entirety of data, because this might increase the false positives that an initial contact detection finds. So we first identify gate sequences as regions of interest and then apply all the other algorithms to it. So we just get the first gate sequence, select the IMU data that belongs to that, just quickly plot that, right? So this is just the IMU data of one gate sequence. Looks like IMU data. We import one of the algorithms and follow the same procedure that we did before, right? We initialize the algorithms, call detect with the information over the gate sequence, and we get, in this case, because it's an initial contact detection algorithm, we get IC list as output. Bunch of initial contacts, right? Without further context, it doesn't really tell us if this is good or bad, but for now we just see we have initial contacts. One thing that might be interesting, most algorithms are quite complicated and have multiple steps. So if something goes wrong, it can be quite hard to figure out what went wrong and how and why. So for many algorithms, we provide additional debug outputs. For example, for this initial contact detection algorithm, which has a pretty complicated filter step, we provide as a secondary output final filtered signal, and you will find the specifics for each individual algorithm in the documentation. Final filter signal gives us basically the filtered output after this elaborate filter step. And if you know the algorithm, you know that each of the peaks here are then correspond to one of these initial contacts. But if initial contacts that you expect are not detected, might be a good idea to go back to that filtered signal and see if this looks as you would assume. So this helps you to basically start debugging problems that you've seen. Let's look at one of the algorithms that are further down the line, namely stride lengths. I already hinted that stride lengths need a couple of more things, but I want to simulate maybe your discovery experience of that. So we already know that stride lengths might need the previously detected initial contacts. So we initialize the algorithm and call it as before, and we get an error, right? This is expected because we already saw in the documentation that sensor height is required. But I just want to show you, okay, if I don't do things the right way right away, whenever possible, we try to make sure that you get the errors that you expect, get the auto-completion that you expect, get the IDE support that you expect, by just following proper Python conventions. So, okay, we need the sensor height. And if you remember, the sensor height was one of the parameters that we had available in our metadata. So we just get it from our metadata and pass it as well. Okay, now our stride length algorithm works, kind of. We see we get output, but the last value is a none. And we also get a warning that tells us that usually we expect that the stride length algorithm assumes that a gate sequence starts with an initial contact and ends with an initial contact. However, the gate sequence data that we provided and the initial contacts that we provided, they don't match quite up. So there's a little bit of time before the first initial contact and a little bit of time after the last initial contact, which might not be an issue, but this is basically not the way we designed the algorithm to work. It still provides us some output, but if you want to make sure that the algorithm works the best way possible, we need to fix that. And this is where we basically use a concept called refined gate sequence, which cuts the gate sequence from the first to the last initial contact. We have a helper function for that, of course. Just I want to show you the kind of the potentially even explorative steps if you're working with these APIs. We cut the gate sequences accordingly. We get our results again. Now we don't have a none. Now we don't have a warning. This is how we designed the algorithm to work. this is a good step to jump into kind of the step-by-step pipeline algorithm. Open that in a new tab. This shows one after the other the inputs and the outputs of each kind of algorithm type that is part of our typical pipeline. So gate sequence detection, initial contact detection, laterality, so detecting if initial contact was the left foot or the right foot, gate sequence refinement, I just talked about that, cadence calculation, stride length calculation, walking speed calculation, turn detection, and then putting everything together in a full pipeline and doing a lot of post-processing steps afterwards. This is basically what comes afterwards here, right? So if you want to deeply understand how these pipelines work, this is the recommended route.
Sorry, I don't want to interrupt you. We have a question in the chat. Are these Jupyter
the notebooks
available?
Not in that exact form. What I basically have here, these code snippets, they are directly copy and paste from our examples already. And if specific things are not there yet, I will have them as specific examples in the documentation over the next couple of days, right? So I showed a couple of things here that are not yet part of the documentation that they will be soon. So these specific notebooks will not directly be part of the downloads, but as I mentioned at the beginning, always kind of go back to the original documentation. And these examples here are basically what I'm showing as well, just regrouped a little. The last thing I want to show you about algorithms is just a little dump of how this would look like in a real pipeline. So we only ran the ICD, so the initial contact detection and the stride length calculation on this single gate sequence. But usually, of course, we want to iterate over all the gate sequences. Then we need to combine all the results together. We realized early on that this is actually kind of complex to make sure that like the initial contacts and samples, that they line up correctly, that their offset is corrected correctly when you combine the results together. So we built also a relatively generic construct, but in its default way, it supports our main pipeline, which we call a gate sequence iterator. And you can see here, the gate sequence iterator allows us to iterate over gate sequences, allows us to properly refine gate sequences, and basically just write out the results that we want to have. And using just a gate sequence iterator, which is kind of in the heart of all of our pipelines, and then looking at the results, you can see that it combined the results of all gate sequences together while making sure that the time-based parameters are correctly adjusted to be relative to the start of the entire recording and not the start of the individual gate sequences. Hopefully, reducing the complexity of kind of the wrapper code that you have to write. And this goes for the stride length or for the initial context or even other parameters that you might individually calculate. There's a way to configure kind of how you expect these adjustments to happen. Okay, this is about algorithms. Important takeaway, algorithms take very, very simple inputs. Okay, algorithms just take the pandas data frame and the value of a sampling rate and the value of the sensor height, right? For example. So if you are able to convert your data into these formats, right? If you have a CSV file with your IMU data and you load it with pandas, then you have it already in the kind of the correct format. Then you can use these individual algorithms. The second important part is running entire pipelines. Right? So entire pipelines are one abstraction level higher. They run multiple algorithms in sequence, running this gate sequence iterator internally, running multiple post-processing steps and so on. Or, so what I'm going to show here is a pipeline that basically runs the entirety of it. But we also have pipelines that do things like running only the stride length block in isolation, but mocking all the previous blocks with results from reference. So whenever we have more than just calling a single algorithm, we call these things pipelines. The thing is, pipelines often need a lot of inputs. This could be the metadata that I need, like the sensor height that I need for a specific algorithm. That could be the cohort the participant is part of to automatically switch with algorithms we use underneath the hood. And this means that the list of parameters that you would pass to the actual method of a pipeline could get relatively long. So instead of doing that, and also to enable a lot of these higher level functionalities that I showed you earlier, like doing the magic crit search, running cross-validate, we basically using a different kind of a more higher level unified data format. In this data format, we call it data set. A data set is a Python class, and I'm going to show you a couple of examples of that in a second, that knows what recordings are part of the data set and has the logic implemented of how to load, let's say, the IMU data, the participant metadata, and so on, once you selected a single recording in the data set. So you've already seen that before. This lab sample data set has this index, right? So these are, as I said, the information of what data is available, can be iterated over, can be selected on, and then we have these individual ways of how to load the data. In the example before, I did that as part of the notebook. I extracted the IMU data as something separate. When we're working with pipelines, we basically assume that the pipelines do that internally. So we expect a certain structure of the data set so that it's compatible with the pipeline. And we expect a certain structure of algorithms so that they are also compatible with the pipeline. Okay, so important takeaway, if we have pipelines, they get not a data frame or a value, they get an entire data point, which is a data set with just one row as input. So let's see how this works. We import one of the pre-configured pipeline, the Mobilise impaired pipeline. I'm going to talk a little bit about what these mean in a second. Like an algorithm, we initialize it. And what we can see is that this has a bunch of stuff pre-configured. If you, for example, look at the pipeline impaired stride length calculation, so this is the algorithm that will be used under the hood for stride length calculation, you can see that this is an instance of the SL Sykes-Store algorithm that I showed you before. We could similarly look at what is used for gate sequence detection, and we see, okay, it's a GSD Ionesco algorithm with these and these parameters. So to run that pipeline, we take an entire data point. So we're not extracting explicitly the IMU data. We just throw long test, so which was the thing that I created up here, into that, let the pipeline run, and then we can extract results as attributes on the object as before. So per walking bout parameters show us parameters per walking bout, and we have secondary outcomes, or not really secondary, but alternative outcomes. For example, we have the aggregated parameters, which aggregate the parameters over all walking bouts that were in the recording. And we have also outputs per stride or per second, depending on what you want to work with. It's quite important to understand where they come from, to understand if they are post-processed or not, but this can all be found in the documentation. So one thing that might be interesting, so we just threw an NS participant into the Mobilise pipeline impaired. What would happen if you throw a healthy adult into the Mobilise pipeline impaired? Actually, it works, but we get a little warning that tells us, okay, this pipeline that was not originally designed or validated to be used with healthy adult participants. This would also happen if your data doesn't have a cohort assigned to it. So this is just a little reminder that we can only, not even guarantee, but we can only give you an estimate of how good these algorithms are, or if they work at all, if you use them in the way we kind of designed them to use. If you're using them for data sets that have completely different participants, for sensor positions that are not what we validated for, or if you changed any parameters of the pipeline, of course you have the flexibility to do that, but then you're out of the realm of what we validated and what we ask you to call demobilized pipeline. If you're interested about the semantics of that, there's a little bit longer explanation to be found in the README. But basically, to make sure that, in particular in the scientific community, there is no confusion between the individual algorithms that are available via the mobcap package and the algorithmic pipeline that we validated with the parameters that we fine-tuned as part of the Mobilise project. We just would like to ask you to just make really clear when you're using that, what you used, and basically call things demobilized pipeline if you used it in the same way that we used it in the project, and calls other things kind of derived based on or using algorithms from the mobcap package, just so that there's no confusion of kind of what performance expectations is associated with your algorithmic pipeline. Okay, so you will see there are a couple of these reminders sprinkled around the pipelines, you find them in documentation, you can find them in warnings, and so on, just to make sure that you don't accidentally do something wrong. But just to see that this works, if you use the healthy pipeline with healthy participants, then we don't get a warning, and we actually get quite different results, right? So before we only detected a single gate sequence, here we find a bunch of them. But just to visualize that there are clear differences between these pipelines. And if you use a different pipeline, you get completely different results. But of course, if you have a large study, you might not want to like deal with that. So we also provide a concept called Mobilise meta pipeline. By default, it basically switches based on the provided cohort. That's also a piece of information that's available on the data point and uses the correct pipeline. You could even configure it. So if you are in the customization side of things and the research side of things, you could configure it to also take additional pipelines and switch depending on the cohorts that you have available. But by default, we're basically switching between all the cohorts that we consider minimal impaired gate and the cohorts that we consider like highly impaired gate. So if we run that pipeline on a healthy trial and then look at the debug output called pipeline name, we see that, okay, the healthy pipeline was run. And if we do the same thing on long test, if you remember that was from the MS participant before, we see that the impaired pipeline is. And finally, this is something that basically the first thing that I showed you, we can iterate over these objects relatively easily and then aggregate parameters we want. Or we can use, just to jump back, we can use these higher level concepts, cross-validate, grid search, or other things that are available either via MobGap directly or via the TPCP package that we use as the foundation for a lot of these optimization tooling to kind of throw pipelines and data sets into these higher level things and do a lot of complex things without kind of needing to specifically manually. Okay. That was showing you how algorithms work, showing you how pipelines work. The thing that I haven't really touched on, and which I only will briefly touch because you will realize that this will be very, very individually, is how to turn your own data into such a data set. Of course, we are not going to leave you on your own with that, but we have basically multiple guides on that. The first, of course, is common data sets and coordinate systems. You need to make sure that your data has the units that we expect. So if you're passing, for example, acceleration data in G, then a lot of algorithms will not work because we expect acceleration data to be in meters per second squared, right? If the x-axis of your sensor points down instead of upwards, a lot of algorithms will not work. So you need to make sure before you use the pipeline that you know how you can transform your data into these data structures that we expect. And then you can have a look at the example on custom data and data sets, where we basically explain step by step the mental model on how to understand your data, understand the requirements, and then loading the data in a structured way so that at the end, and I'm going to show you the end result, we can put it in one of these dataset classes. Let's zoom out a little bit because there's a couple of more lines of code. But at the end of the day, this is a dataset class that is built out in this example that can load kind of an arbitrary file structure of data that is stored in CSV files. And if your data is stored in a feather file, in an HDF5 file, is named in random various ways, then this might change slightly. But I just want to give you the feeling that if you want to adapt your data set or your code structure to work with all of these amazing tooling, then this will take around like 100 lines of code if your data is simple, and a little bit more if your data set is more complex. If you run into any problems with that, we have that example that is relatively specific for MobGap, of course. But this idea of data sets stems from the underlying TPCP library, which has a bunch of more guides on related topics, for example, how to cache data while you load it, or a lot of other examples of how these data sets can be structured. And we have kind of as a reference, we have an entire additional library that was built for GateMap, the other library, if you remember, has just dataset classes for different publicly available datasets for FUT1 IMUs. But of course, like these can all be served as reference of how to implement dataset classes in general and make them compatible with Mocha. If there are still issues, and this is kind of the general message that I want to convey, this is an open source project. And as an open source project, we have an issue tracker and we have a discussion forum here. We can already see like, there are not many discussions happening yet, but people have started asking questions here. And myself and other people from the developer team will try to respond to that as soon as possible. If you're interested kind of in following the development, you can head over to GitHub. If you have a GitHub account and want to get regular updates when we update things, it's possible to star and enable notifications for the repository. Then you will get notifications if we publish a new release. If you are not that interested in things, I would just recommend to check back every couple of months. When we create a new release, and that is quite important because I mentioned at the beginning that things might change, we accompany that with an extensive change log of what has changed. So even if you start working with the library today, and we change a couple of things, rename a couple of things in the next couple of weeks, you will be finding that information in the change log so that you know what to update and what to change. And as the pipeline progresses, as the package progresses, of course, these breaking changes will become less and less. To give you a timeline on that, our plan is, as I mentioned at the very beginning, to finish all the core components till end of June, and then start a phase where we focus on revalidating the algorithms. And it could happen that during that time, we realize, oh, that doesn't work as expected, either from a scientific perspective, or, okay, that's not easy to use when writing validation code. You might change the ergonomics of that a little. Okay. This was everything that I wanted to show you. So now we have like approximately 30 minutes left that are for free Q&A. So either ask me to show a couple of more like specific things or free-flowing questions, either about how to implement, how to work with that, and so on. Okay, there is one question that is incorporating the CVS, or the clinical validation study dataset. Okay. Let's quickly talk about data releases, even so they are not, that's not like core part. Brian, do you want to jump in for that, or should I just?
Yeah, just to clarify, the entirety of the source data from the CVS data set is not scheduled for release. We are releasing the data from the TVS, but not the CVS. We will be releasing some of the DMO, aggregated DMO results from the CVS, which is a significant data set, but not the source data.
Yeah. So yeah, so the if you're part of the Mobilise project and or have access to data from the CVS, then we have tooling to load that because it's part, like it follows the same standardization than a lot of the other data follows, but we don't have that direct public high-level support as we have for the TVS data, which will be published early July. So when that is available, this running everything in one line, as I showed here, will work. But if you have access to the clinical validation that the study raw data, it will be similarly easy. Yeah, but once this gets finalized and also like Mobilise internal data structures for that become more clear, you can of course look into better supporting that as well. What dimensions are the input data? Okay, I'm not 100% sure what you mean by that, but just give you a couple of potential answers to what you mean. So like raw data, IMU data is, we have accelerometer and gyroscope, so we have 6 columns, number of samples. And for these things with data sets, we do a little bit of clever magic in the background. We're not loading the 2.5-hour data from all the 105 participants into memory when you create a data set, but we only do that once you load the individual like recording. Otherwise, probably your RAM would explode. I hope this answers the question. There's an important question is maintenance. So there are two answers to that. Number one, there are specific tasks that we are still planning as the direct continuation of Mobilise-D, which is the revalidation. And for this time, there will still be like actively people working on that. But we will also spend that time to figuring out how a longer term maintenance plan could look like. Of course, like with open source projects, it's always a question of funding, right? Can people still justify working on that, even if the primary funding source is not available? And of course, we will hope that we will find a mentor. But this is also a reason why we wanted to make this open source. If you are actively working with that, in particular, if you're working in a company and you're getting paid to work with our library, we would, of course, ask you to think about like if there are ways for you to contribute back and to support the continuation and the further development of that library. If you are in a position to do that, feel free to contact us. Like we can talk about that and think about potential ways. But we are actively like thinking about that and weighing different options. Yeah, so I can't give you a like concrete answer, but just that we will make sure that it will work. Can you give a quick overview of how MobGap and GateMap are related? Yeah, I can do that. So generally, they are two independent projects. The reason or the main core point of how they relate is through the underlying library. We're gonna let me just search for it. It is through the underlying library TPCP that we use to structure the individual algorithms. Sorry, a couple of clicks away. TPCP, right? So this is the library that you saw a little bit. That handles the optimization, that handles the set params function and so on. So this is the core, the common ancestor of both libraries. Because we have that common ancestor, the algorithms are actually like intercompatible. Doesn't mean that you should do that in the sense that I'm not sure if a lower back algorithm would make any sense to be applied to foot IMU data or the other way around. But they're actually intercompatible in a way that we are using some of the GateMap lower level algorithms as part of MobGap. For example, the Madvig implementation. So for the Madvig orientation tracking, we are using the one from GateMap directly. We are not planning to merge the two because they're still like somewhat different, but this level of intercompatibility should remain so that in case you have situations where you want to use both, it should theoretically be possible. The reason why we don't want to merge it is again a matter of complexity and a matter of like who is responsible for what, right? So if we as the machine learning and data analytics lab from the FAU want to continue to add our internal algorithms to GateMap and want to bring that in one direction, these interests might conflict with what the continuation of the Mobilise consortium wants to do with MobGap. So we want to make sure that everyone has all the freedoms on continue and push these projects into different directions. Magnetometer, there are no algorithms that actively use the magnetometer. But the data is passed through these structures. So if you would implement a custom stride length algorithm that would make use of the magnetometer, the data would reach the algorithm and your algorithms could do things with it. But the algorithms that we have are designed to work without magnetometer. Do we plan to add other algorithms? This depends on kind of this idea of support that I tried to answer earlier, right? If there's a lot of interest from the community, then we can look into adding additional pieces to the library. But at the end, we will not add things just for the sake of it, because like resources are limited and time is limited. But if the hope is that if people think that is a good starting point for their own validation and they used that to implement their own custom algorithm, then please like notify us like, hey, look, I implemented an algorithm that's compatible with MobGap. Are you interested in merging that and adding that officially? And then we can talk about that. So if there's interest, we hope, of course, that this will grow into more of a community developed project with more algorithms added over time, but we cannot promise or guarantee that. Are there different pipelines for different cohorts? This comes back to the slide I showed earlier. So the pipelines are almost identical. There are different algorithms used for gate sequence detection and for cadence estimation. So these are really different algorithms, no, not just different parameters. So the pipeline kind of diverges at these aspects. Could you please describe the possible use cases? Is it more suitable for detecting walking bouts from clinical tests or home settings? So the validation that we did for the algorithm, if you look at the paper that's like the Cameron Kirk paper here, that there we show the performance metrics for in-lab as well as unsupervised home recordings. As you might expect, unsupervised home recordings are always more challenging. So errors are slightly higher in these unsupervised tasks than they are in highly controlled lab environments. But very importantly, the mobilized algorithms from the ground up were designed to be used in unsupervised home recordings and not just in lab recordings. So we expect the algorithms to work in both scenarios, but of course, have a look at the papers that we published to get a feeling for the performance range and if this is suitable for whatever you are doing. How much work? Okay. Arne Müller asked, like, how much work would it be to replace things and basically how to integrate individual algorithms. This is something I haven't touched on in detail, but I can show you a little bit of that. So I would say there are 4 different levels of how I expect you to modify things. Let's go back here. Number 1 is you want to modify a parameter of, right? Let's say you want to keep the algorithm, but you want to modify the filter order of the pre-processing filter of XYZ, right? Then we just use set parameters, like I showed earlier. We can basically deeply configure the nested objects. Like we could go in here and do min, what was it? GS length, I don't remember, seconds, and set that to 10 seconds, right? So we could deeply modify parameters. In the same way, this is what I showed earlier, we could replace an entire nested algorithm. So here, that would change out the entire gate sequence detection algorithm. That would kind of be level 2. And I can tell you in a second a little bit more about how you could implement a custom algorithm here. And kind of level 4 would be, oh, level 3, maybe I only have 3 levels, I'm not sure. Oh, wrong library, MobGap, is if you look at the implementation of these pipelines, or even of the individual algorithms, they're like around 200 to 400 lines of code. So if you decide that whatever you want to modify is like a deep change of how the structure works, but you still want to keep certain things, then I would just recommend to basically go ahead and copy and paste the core component and change whatever you like. This important thing is, as long, and this then goes into the direction of how you could develop your own algorithms, as long as you're using the same base classes and follow the same convention of how input and output should look like, whatever you build will be compatible with all the other structures. So just to give you a quick idea of that, a gate sequence detection algorithm, so if you want to implement your own, needs to be a child class of base gate sequence detectors. A little bit too loud. Yeah. Needs to be a child class of base gate sequence detector, needs to implement a detect method, and needs to output a parameter that's called GS list. If you're doing that, if GS list has the correct format at the end, then you could do that and replace this call here with an instance of your custom algorithm, and the rest of the pipeline would still continue to work, right? So this is very much a use case that we will support. And very importantly, if you're implementing your own algorithm, you don't need to touch our code. You could still keep using MobGap as a library, and you don't need to like start modifying the source code. You can all do that as part of your project without needing any change to the core library. Okay, that were all the questions that were directly asked. Are there any further questions, comments? Yeah, as I said, like reach out if you have questions. Preferable, ideally, via the issue tracker or the discussions, because then these discussions and solutions are public. So if people have similar questions, they can find the answer there. If for some reason the question that we have is confidential because it's about integration of like internal data, which structure you cannot share, of course, feel free to also reach out by email, but I want to heavily emphasize that the preferred way is through these issues and discussions. And this maybe like on a positive note, if you successfully work with MobGap, also let us know. It's always nice to hear that people are using that, because we put it out as open source. It's sometimes hard to track if people are actually using it and working with it, or if they just tried it, didn't work, and just never came back to it. So yeah, if you're using it successfully, we're also happy to hear about that. Yeah. From a scientific perspective, at the moment, there's like, we have a recommendation of how you might cite the package and the underlying algorithms if you're using that in your publication. This might change once we have some form of scientific publication that might be targeting the package directly. So if you're using it, we would highly appreciate if you kind of check out how we would like that work to be cited, so that, yeah, we can also track these metrics in an ideally official way.
We have one more question, sorry. Somebody that joined late and asks, what is the IMU data format? The timestamp.
What is the IMU data format? So we don't need the timestamps. We, like all the algorithms that we have implemented, are assumed to be like sampled in a continuous way. So you need the data and the sampling rate, and then it's just one row is one sample, like that. Yeah, and we have documented that in the user guides. Yeah, the user guides, common data types, where it's explained in detail what units we expect and how the format should look like. Arne asked, how many lines have we written for MobGap? That's a good question. I think it's a couple of thousand, but I don't have an exact count. There's a bunch of like auto-generated files in the repository as well, which makes counting a little bit hard. Yeah, and of course, and this is a positive thing, most of the lines that we've written is documentation and tests and not actual logic, which is a good thing. So maybe core logic is a couple of thousand lines, and then at least that in documentation and tests. And we are planning to particularly add to the documentation part now that we have figured out all the complex stuff. Another question. Is the algorithm for lower back IMUs, Wishbone IMUs? So the question was if the algorithms only work for lower back IMUs and whether the pipeline is also working for Wishbone IMUs. So the pipelines and algorithms are primarily designed for lower back IMUs. We have not directly tested them on Wishbone IMUs with a little asterisk. I will talk about that in a second. So if you use them, sure, but probably it won't work. So you would need to do your own proper evaluation of that before you should use that for anything serious. The little asterisk is Felix Kluge, who is working at Novartis, has recently published a paper on comparing different gate sequence detection algorithms for wrist-worn IMUs. And he also tested some of the sensors that were originally designed for the lower back, some of the algorithms that were originally designed for the lower back position on the wrist, and they performed somewhat well. Please check out the paper and see if the algorithms that we have implemented work for that. We at least not officially claim that they work for that position, and for most, I would assume they don't.
Thank you, Arne, also for telling us and telling the people here in the webinar how to cite and how to get to the data. It's very important also to be used, tested, and also if you have more questions to come back to the team that you see here, to Arne or Brian, to ask. You'll have their contacts also on GitHub, and then you can interact with them. Brian, would you like to say something more? I see that you're active.
The last thing I'd like to do is to thank Arne and the team for an unbelievable amount of work over the last 6 months or so. The work that Arne is describing today was work that was not originally in our program of work for Mobilise-D. It's something that, you know, we realized would be a very positive thing for us to do at some point during the last summer. And when Arne was approached to possibly take this on top of the already significant workload that he had in the project, he was very enthusiastic about it. And I think the results are very clear to see today that the team has done a fantastic amount of work.
Thank you, Brian. And yeah, I hope a lot of you will have the chance to use it and have a positive experience in using it. And yeah, use it. And if something doesn't work, let us know. If something doesn't fit your requirements, let us know. Yeah, so try it as early as possible. And then if things don't work out for you, we can potentially still change things so that they work better for you. So don't wait until basically everything is done. We don't have funding anymore to continue it. Then the chances of like making major changes might be smaller. So yeah, try it out and let us know how it goes.